everybody and welcome back to my channel. Today we are finally wrapping up the series called Turning Recursion into Goto Labels. And to cap it all off, we are going to finally build a function that actually returns something rather than void, which just eliminates a lot of complexity right off the gate because now you don't have to keep track of that return value of your function origin or call origin. So to give you some context and for you to get up to speed, make sure to watch the part 1 of this video and the part 2 of this video. So in the first video we introduced something called call frame, which is used for stack manipulation in order to translate our recursion into Goto labels, because at the end of the day we were trying to literally translate recursion into Goto labels. So here's our struct for this call frame, and contains the arguments of the function and the return value of the function, or anything that we will need in order to pull that off. And one of those things is, of course, and it is essential to have the origin, and that which represents the point of memory or the computed go-to where we need to jump to once we return from our function. So enough of that, let's jump straight to what function we want to turn into Goto labels. So this function, I picked this function because I find it intermediate. It's not complex, it's not basic, but it's rather intermediate. It's not one function call, it's two function calls. We're still using binary tree, and this function will sum our binary tree, where we don't need to have particular order because it is addition after all. And first we write and I mentioned this in the previous videos of this series. First, you write your C++ recursive approach, and then usually you take the assembly of it, and then you rewrite your own solution, or by looking at the high level function, you can pull off that translation. So here we have pretty standard stuff which we've done before in the previous videos, but the crux of the matter is, how do we return a value from our function call that we are trying to simulate? Well, it's quite simple. The same way we access arguments, by accessing the last element of the stack, of the call frame stack, that is the same way that we would modify that particular call frame in order for it to contain and include the return value. So our return here is essentially the translation of the return there. So the most important factor here is to keep track of your stack, not to be confused with stack trace. So here we just have pretty standard stuff, like I said, where we make a call to our function, which is essentially this. But how do we get what we want from there, the return value? Well, first of all, let's imagine we are running through a binary tree. or in this case, iterating to through a binary tree. First we get a node, and it's not null. We jump to our call here, or our label here, which is essentially our recursion. And then it says return 0. I will not go depth 2 or depth 3 because we're gonna get lost easily without a debugger around. So now we jump to return, and we've added our call origin. We get to the return, we pop the last call of the stack, and we make sure to return to the origin of the call. But before that, we made sure to store the return value in our current call frame, which was this function call. So once we get to the origin, and the origin is treated in this case as stack, not stack -1. So it is, while it is considered to be the last element, it is the last element of the popped stack, so that we can know where to jump to. Once we jump to the origin, the way that we will get our return value is to use the same thing we used here. And with this in mind, we are 100% sure that it's the same call frame that we are trying to access. Because once we pop it off the stack here, we jump to the return, to the computed indirect jump of the return. We know that this is what that function call holds or held. So the way I would access it, so the way for us to access the return 0, or this rather, would be to do this, which is exactly the same of the origin. So that would be the return value of the origin. And because our last element of the stack represents the current call frame, we are going to use stack C-1, which is the last element of the stack, for us to be back to the current function body here. So this function, once it is called or executed, we push the argument onto the stack, or we push the call onto the stack. We process it here, right? We pop it onto the stack and we return. And in that mind, when we popped, at this level, we still keep hold of that call frame. That's why I said here, this is essentially the same as this. You just have to keep careful trace and keep an eye on your stack always, and you can literally translate any recursion into something like this. So that's when we come to this point. At this point we return, right? So how do we return? It's the same as this. We access the current call frame. We make sure that the return value is mutated or modified, and then we get to the next call, and the next call is recursive sum when we try to walk through the right side of the binary tree. So the logic is essentially the same when you call the function as this one. You get the origin, and now this is the bottom line. how do we return from all of this? How do we evaluate this entire expression? Here's how. We've already returned from here, right? Returned from here. We just need to access the current call frame again and make sure to access the return value of the call origin, which returned. And the origin of the return is this. Like I said, that can be seen from this computer jump to that presents not the last element of the stack, but the call that was popped that needs to return. So that's why we are able to do this in such a flexible way. And now once we're finished with this, we jump to the return, this evaluates to true, we go to done. I made sure I included an assertion here. You wouldn't have this in your production level code, of course, but I was testing this function. I was a little skeptical about it because this is the first time I'm doing such a translation, but you also have to make sure anytime there is a translation, you have to unit test it and cover, and your coverage level should be around 10 calls, covering all the edge cases as well, so that you are 100% sure that your function, your translation of the recursive function behaves the same way as the recursive function itself. And what's the better validation of the recursive function but having the recursive function assert your code by itself. What I mean by that is, here's how I test this. I first call my function, that's the translation of the recursion, and then I execute the recursive sum tree, which is the original recursive call or recursive function. And now I'm 100% sure that, okay, with this complex of a structure, if I'm running my recursion properly and accurately, or more so correctly than any of those words, now I'm ready to use it at the production level. Okay, I think that would be it for this video. I will include the source code in the comments. And I think we are sort of diving into some things or some really deep topics about C++ that it's really hard to make videos, and it's really hard to explain this kind of stuff because most of this, to me at least, is most of it like a tacit knowledge. And at the end of the day, we always have to read the code. So these kind of things are really complex, and at the end of the day, you have to rely on the code more so than something you can verbalize. Just like Linus said, you should understand programming languages like your natural language, like a verbal language. So at the end of the day, we have to read the code. It's sometimes it's not possible to make a video out of it or an explanation out of it. You just have to read it. Anyway, that would be my cue if you want to take it from me, but that's as far as I go. Alright, thank you for watching, and see you in another video. Take care.